In this example, we want to find and classify the critical points of f of x equals 2x to the fifth times the quantity 2x minus 1 to the fourth plus 7. If we look at this function on Desmos, it doesn't look like we have any local extrema. And if we played around with zooming in and zooming out, it might take us a while, and we aren't even sure if we would get the exact locations of these local max and min. That's where we really want to go to our derivatives and not rely on technology. This one is a very long problem, so we're going to skip some steps. So feel free to pause to do your own work and see if you can get the similar answer that we're going to get. Now, the thing is the only critical points are for this particular one is when f prime equals 0, because this makes sense for any x. F prime is always defined. So we're going to set this equal to 0. We have a 2 that we can factor out. We have 4 x's. We have 3 2x minus 1's. So we're left with 5. We're left with 1 2x minus 1. So we're left with an 8. So we're left with 1x. This simplifies to 18x minus 5. I get 0. X equaling 1/2. 18x minus 5 equaling 0. 5/18. So now what we want to do is we want to classify all of them. And we want to determine whether or not any of these are local maxima, local minima, or they might be neither of those. So what I like to do is I like to organize my work when I'm doing the first derivative test. And some people like to organize them as a table. I like to organize them on a number line. So I'm going to zoom in on the number line because these numbers are fairly close to each other. And I'm looking at 0 and 5/18 and 1/2. And I don't have to be perfect as to where they would be on the number line. Certainly if you were to look, this would not be perfect. One thing that's great about this is this is a nice polynomial, nice continuous polynomial. The only way this whole thing is going to change sign, SIGN, from positive to negative is by going through 0 first. So these are the pieces, the only pieces we need to check. And we only need to check on for one number on any side of these. So I can pick any number less than 0. And that's why I have a number line. And so I might choose -1. You might have chosen -5. It's not going to matter. It's just whatever you choose might make it more or less difficult to figure out what's going on. And what we're looking at is and we're going to focus in on f prime of x, and I'm going to look at it completely factored. So I'm going to rewrite this, that this is f prime of x, completely factored. That's a 4. And I'm going to focus on when I plug in -1 here, are we getting positive, negative? I don't care about the actual numbers, and that can speed things up. Even punching in the buttons on the calculator might be longer than actually doing this process. And the more you practice, the quicker you'll be. So if I plug in -1 into each of these pieces, is it positive or negative? And I'm looking at f prime, so I'll label that. And when I plug in -1 here, because it's to the 4th power, that ends up being positive. When I plug in -1 here, right, don't be afraid to write things down a little bit. This is going to be negative. And when we plug in -1 here, we're going to get -18 minus 5. Excuse me, do I care what the actual number is? No, I only care that it's negative. So I have a positive times a negative times a negative. Excuse me. That makes the overall f prime is positive. Now, what does that do to the graph of f? That means f is increasing. And I like to draw this because when I look at the chart overall, they can visually help as far as what is going on with all of this information. For this one, I need to find a number between 0 and 5/18. They're not ideal numbers. You might choose maybe 1/18. It doesn't have to be exactly in between. It doesn't even have to be a fraction, but the 1/18 might be easier for calculations. And again, I'm going to go a little bit faster. If I plug in 1/18 here, I'm going to get a positive 1/18. That's going to end up being 2/18 minus 1, or 1/9 minus 1. Quantity cubed stays negative. And when I do 1/18 here, I have a negative. So f prime is still positive. We are still increasing for the function, the graph. Which makes sense because we only changed from positive to negative numbers right here. To the fourth was positive to the left of 0, positive to the right to the 0. Stayed the same. Number between 5/18 and 1/2, otherwise known as 9/18. So we might choose 6/18, otherwise known as 1/3. Right? 7/18, 8/18, any of those would be fine to use. And other numbers work too. All right, if we plug in 6/18, I don't care what the actual number is. I just only care, I certainly don't know what it is to the fourth. Certainly faster to realize it's just positive than to actually calculate it on a calculator. 6/18 might be easier to see it as 1/3 when we plug it in there. It's negative. And now when we see 6/18, we see this as 6/18. The 18ths cancel. We'd have with 6 minus 5, all of a sudden that changed to positive, making the whole thing negative. For f prime, making f decreasing. Luckily, we're almost done. Some number between to the right of 1/2, greater than 1/2. Many people might have thought 1. Could have used 10. Doesn't matter, anything to the right. 1 is easier for calculations. We get positive, 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 making f prime completely positive, and f is back to increasing. Now when I see this, the first derivative test tells us when f prime changes from positive to negative, we have a max. Okay, we could memorize that, but visually that means we have something like this going on. This one's easier to see. We have, when I see the arrows, we have a local max here. And when f prime changes from negative to positive, f changes from decreasing to increasing, so we have a local min. And here we were increasing briefly the horizontal tangent line and then increasing again as far as local extrema. That means neither. Okay, we're looking at this back on Desmos, and I've created a table with the values of our critical points, and we want to focus right around 7. So 6.99 for the y values until maybe 7.001. And looking at this, we can finally see the effect that we saw, the calculus showed us that here we had a local max,